We have ignition. We have a liftoff.
Vehicle response is normal.
This thing came in, moving fast. If this were aliens in some kind of advanced ship, it would be maneuvering, doing interesting things.
NASA's longest living mission ever has just made an impossible encounter after 45 years in space. For almost 5 decades, this remarkable spacecraft has made an indelible impact on cosmic exploration, delving into the depths of our solar system and interstellar space. Despite its limited memory capacity, which is 3 million times smaller than a regular smartphone, the Voyager probes continue to lead the way in space exploration.
He convinced Voyager to turn its camera back towards Earth. Basically amounts to Earth's first ever selfie. And there was this pale blue dot. There's something you don't understand. Doesn't mean the explanation is something extraordinary.
As Voyager 1 nears the end of its operational life, it has made a groundbreaking that will transform what our knowledge of space. What exactly has Voyager 1 discovered? Could the fate of this revolutionary spacecraft lie in the hands of extraterrestrial beings? Join us as we explore how Voyager 1 has made impossible discovery after 45 years in space. If there's one space mission that has made an enduring impact on our understanding of the universe, it's Voyager. The mission was solely dedicated to exploring our solar system, and the Voyager probes far exceeded all expectations by venturing into uncharted regions of space. Voyager 1's remarkable journey has been a source of great fascination for the scientific community, providing a lot of valuable data about our cosmic surroundings. Today, 5 decades after its monumental launch, the Voyager mission continues to hold the record as the longest-running mission conducted by any space agency worldwide. It is truly astonishing that this space probe has defied initial predictions, which estimated its lifespan at only 5 years. However, what many people are unaware of is that Voyager 1 encountered a major setback during its launch when one of the rocket stages malfunctioned, requiring significant last-minute adjustments to prevent mission failure. NASA's engineers quickly responded with their expertise, eventually resolving the issue and allowing Voyager 1 to catch up with its twin probes in space. Yet now, after decades of successful operation, Voyager 1 faces a new challenge, one that defies conventional explanation. Keep watching as we delve into the possibility of extraterrestrial involvement and unravel the mysteries surrounding this shocking discovery. But before we dive into all the fascinating details, let us first establish some important context. In the 1960s, after the United States lost the robotic race to the moon against the Soviet Union, there was a shift in the focus of space exploration. The moon and space dominance were still incredibly appealing, so the attention turned towards a more popular and well-funded manned program. During that time, unmanned exploration took on a supporting role, with missions like Ranger and Lunar Orbiter paving the way for future Apollo missions. However, the idea of exploring other planets captured the imagination of many, coming in second only to the excitement surrounding the Apollo missions themselves. As a result, the unmanned exploration programs naturally progressed towards the next step, exploring other planets. Looking back, some people tend to overstate the scientific importance of unmanned programs compared to the political and technological goals of manned flights. They argue that the robotic missions were more scientifically pure in design and intent, downplaying the scientific achievements of manned missions. However, what truly captivated and ignited the passion of the American public was the promise of capturing photographs of the planets. It was the prospect of seeing those images that sparked the greatest interest and enthusiasm during the golden age of spaceflight. While the importance of magnetospheric physics and gravimetric studies cannot be denied, it was the quest for planetary photographs that truly resonated with people. On September 5, 1977, a spectacular spacecraft was launched from Cape Canaveral, Florida, which is renowned for its testing of missiles and space probes. This event marked the beginning of an incredible journey as Voyager 1, a spacecraft, was launched into space. Interestingly, just 15 days earlier, its twin, Voyager 2, had embarked on the same cosmic adventure. Their mission was to explore the gas giants of our solar system, Jupiter and Saturn, along with their orbiting moons. Little did anyone know that these intrepid explorers would surpass their initial goals and venture to the farthest corners of our celestial neighborhood. The Voyager twins were equipped with cutting-edge technology, even by the standards of their time. From their engines to their propellers and antennas, everything was meticulously designed for durability. NASA drew inspiration from the Mariner spacecraft, but added intriguing modifications. The accomplishments of these Voyager probes have been nothing short of spectacular. More than 40 years ago, their early observations of Jupiter and Saturn's moons left researchers amazed and shattered preconceived notions about these distant worlds. These moons, once thought to be desolate and pockmarked like our own moon, turned out to be teeming with geological activity. Voyager 2, in particular, achieved several remarkable milestones during its journey. In 1986, it became the first spacecraft to pass by Uranus, and only 3 years later it conducted a flyby of Neptune. To this day, Voyager 2 stands as the sole spacecraft to have embarked on such a path. As these spacecraft continue their extraordinary voyage, NASA has implemented measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been deactivated to conserve energy. This strategic move ensures that the Voyagers can continue functioning well into the next decade, with an estimated mission end date of 2030. For the scientists and engineers who have been integral to this extraordinary journey since its inception, the culmination of the Voyager missions evokes bittersweet emotions. Their unwavering dedication and tireless efforts have carried the project far beyond its initial expectations. The data transmitted by the Voyagers has yielded invaluable insights, fueled countless scientific discoveries, and ignited the imaginations of researchers and space enthusiasts across generations. It's important to note that Voyager 1 and Voyager 2 were not ordinary spacecraft. They were meticulously designed to be stable platforms, with a rotation rate more than 15 times slower than the hour hand of a clock. This deliberate design choice minimized any blurring of images and data as the spacecraft hurtled through space. Their impressive imaging capabilities never ceased to astonish scientists and the general public, even before their encounters with the outer planets. The spacecraft began beaming back images of Jupiter, while still several months away from the planet. These early images, showcasing the swirling clouds and the famous Great Red Spot, brought sheer delight to the folks at NASA's Jet Propulsion Laboratory. But it was the discovery of active volcanoes on Jupiter's moon Io that really stole the show. Io, a little bigger than Earth's moon, turned out to be the most volcanically active body in our entire solar system. The spacecraft's instruments detected some peculiar signals emanating from Io, and the vivid images they captured confirmed the findings. Those images unveiled towering volcanic plumes and a surface marked by the ejection of volcanic material. One of Io's prominent volcanoes, Pele, has even erupted 30 times higher than Mount Everest, blanketing an area nearly the size of France. In total, the Voyager spacecraft snapped over 33,000 images of Jupiter and its moons, revealing the planet's stunning beauty and the incredible diversity of the Jovian moonscapes. Before we dive into the recent mind-boggling discovery, let's not forget that the twin Voyagers have been uncovering breathtaking findings since their launch. One of the most astonishing revelations was the existence of Jupiter's rings, which, although faint, added an extra layer of intrigue to the gas giant. On top of that, Voyager 2 unveiled the icy shell of Europa, one of Jupiter's 53 named moons, believed to be over 60 miles thick. These findings challenged our previous assumptions about these far-off celestial bodies and sparked further investigations into the potential habitability of icy moons. As the Voyagers bid farewell to Jupiter, they received a gravity assist that gave them a vital boost, propelling them towards Saturn. Without this nifty push, they wouldn't have escaped the sun's gravitational pull and ventured deeper into space. Voyager 1 and Voyager 2 then went their separate ways, each heading towards new frontiers. Voyager 1 embarked on a trajectory that brought it close to Saturn's moon Titan, enveloped in an orange, hazy atmosphere. The mysteries surrounding this moon piqued the interest of scientists, leading to more studies on its complex chemistry. Voyager 1 then veered northward, departing from the plane of the planets, and began its epic journey beyond the boundaries of our solar system. Meanwhile, Voyager 2 embarked on a series of thrilling adventures that took it to the outermost planets of our cosmic neighborhood. In 1986, it made history with a flyby of Uranus, where it stumbled upon 10 previously unknown moons, increasing the planet's moon count. 3 years later, Voyager 2 reached Neptune, unveiling the extraordinary features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, making it the fastest wind ever observed on a planet within our solar system. As the spacecraft zoomed within 2,980 miles of Neptune's azure, methane-rich atmosphere, it provided unprecedented insights into this remote world. Neptune's largest moon, Triton, turned out to be one of the chilliest spots in our solar system, with surface temperatures plummeting to a bone-chilling -391 degrees Fahrenheit, -235 degrees Celsius. Triton also boasted unique characteristics, including ice volcanoes that spewed nitrogen gas and icy particles up to 5 miles high into its thin atmosphere. These discoveries expanded our understanding of the incredible variety and complexity of celestial bodies, even in the farthest reaches of our cosmic neighborhood. One individual who played a pivotal role in extending the missions beyond their initial goals was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing one last set of images before shutting down the cameras on both spacecraft. These images would serve as a parting gift to humanity, offering a final glimpse of our home planet from the distant depths of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back towards the inner solar system and snapped a series of 60 images. The most iconic among them, known as the pale blue dot, remains an indelible symbol of our place in the cosmos. Taken from a staggering distance of 3.8 billion miles, it stands as the farthest image of our planet ever captured. Earth appears as a minuscule pale blue speck, barely discernible amidst the vastness of space. At the heart of the Voyager mission lies an extraordinary relic, the enduring 8-track tape. Picture it as a time-traveling artifact, a treasure chest filled with invaluable scientific knowledge, hurtling through the cosmos. The 8-track tape recorders used on the Voyager probes were not your typical consumer cartridge tapes. They were a reel-to-reel storage system designed by Lockheed and manufactured by Odetics Corp. These machines were quite impressive in terms of their specifications. They used a belt-driven mechanism and employed a 1.076-foot, 328-meter, long reel of 1 2-inch, 12.5 millimeter, wide magnetic tape. The tape had 8 separate tracks for recording data. The recorders had 2 different recording speeds available, 115.2 kilobits per second, kbps, and 7.2 kilobits per second. During playback, the maximum speed was slower at 57.6 kilobits per second, but there were also options for 33.6, 21.6, and 7.2 kilobits per second playback speeds. You might be wondering why there are only a few expeditions as successful as this mission. It's time to get into that. What strategies were employed to guarantee the success of the Voyager missions? Almost 50 ago, in August and September of 1977, a band of humans launched a pair of robots to explore the solar system and probe the infinite darkness beyond. To achieve their goals, these brave spacecraft employed a clever technique called gravity assist maneuvers, which played a crucial role in their legendary missions. Think of it as a cosmic dance between the spacecraft and the massive planets of our solar system. Instead of relying solely on their own engines, the Voyagers utilized the gravitational pull of these giant planets to slingshot themselves towards their destinations. This ingenious maneuver not only conserved fuel, but also provided the necessary velocity to visit multiple destinations on their grand tour. Let's delve into the details. Gravity assist, also known as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it passes by. Consider Voyager 1 approaching Jupiter, a colossal gas giant with an equally immense gravitational force. With utmost precision, Voyager 1 was strategically guided to swing by Jupiter at just the right angle and speed. Jupiter's gravity then accelerated the spacecraft, giving it a significant velocity boost, an essential cosmic oomph. However, executing this maneuver requires intricate art. If Voyager 1 had approached Jupiter at the wrong angle or speed, it could have resulted in a catastrophic deviation from its intended course. The level of precision demanded by this maneuver is mind-boggling. Yet the brilliant minds at NASA's Jet Propulsion Laboratory successfully choreographed these celestial ballets not just once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. For instance, Voyager 2 utilized gravity assists from Jupiter and Saturn to reach Uranus and Neptune, making the grand tour possible. The Voyager missions owe a tremendous debt to these slingshot maneuvers. Voyager 1 went on to reach interstellar space, and Voyager 2 swiftly followed suit, all thanks to the precision of these gravity assists. The concept behind gravity assists may appear straightforward, but their execution is astoundingly complex. Voyager 2's grand tour demanded meticulous precision, as missing any of these slingshots could have spelled disaster. Nonetheless, the individuals behind these missions were unwavering in their determination to acquire knowledge and explore the unknown. While gravity assist maneuvers played a pivotal role in navigating the cosmos during the Voyager missions, another critical component ensured their success: the Deep Space Network, DSN. Think of it as the interstellar telephone line that maintained a vital connection with our intrepid Voyager probes as they ventured into uncharted territory. So what exactly is the Deep Space Network? It may not be as glamorous as a spacecraft, but its significance cannot be overstated. The DSN consists of an array of massive radio antennas strategically positioned around the world, including locations in California, Spain, and Australia. These colossal dishes, ranging from 26 meters to an astounding 70 meters in diameter, act as cosmic megaphones, facilitating communication with spacecraft beyond our planet. The Voyager missions have been instrumental in inspiring several spectacular expeditions to interstellar space. However, before we delve into the impossible discoveries made by Voyager 1, it's important to highlight these remarkable missions: Pioneer 10, Pioneer 11, and New Horizons. These missions have made significant contributions to our understanding of the solar system and beyond. Pioneer 10, launched on March 2, 1972, was the first spacecraft to venture beyond the asteroid belt and explore the outer solar system. Its primary objective was to conduct flybys of Jupiter and its moons. On December 3, 1973, Pioneer 10 became the first human-made object to pass through the asteroid belt, providing valuable data about this region of space. It then conducted a close flyby of Jupiter on December 3, 1973, capturing stunning images and collecting crucial scientific data about the giant planet, its atmosphere, and its moons. Pioneer 10 continued its journey beyond Jupiter, becoming the first spacecraft to cross the orbit of Neptune in June 1983. Despite losing contact with Earth in 2003, Pioneer 10 holds the distinction of being the first man-made object to leave the solar system, entering interstellar space. Following in the footsteps of Pioneer 10, Pioneer 11 was launched on April 5, 1973, with similar objectives. It successfully completed a flyby of Jupiter on December 2, 1974, capturing breathtaking images of the planet and its famous Great Red Spot. Pioneer 11 then embarked on an extended mission to explore Saturn and its moons. On September 1, 1979, Pioneer 11 became the first spacecraft to fly by Saturn, providing unprecedented views of the planet's rings and collecting vital scientific data. The mission also revealed new information about Saturn's atmosphere and its moon Titan, which was discovered to have a thick, nitrogen-rich atmosphere and the potential for organic chemistry. Pioneer 11's successful mission to Saturn expanded our understanding of the gas giants in our solar system and their diverse moons. Moving ahead to a more recent mission, New Horizons was launched on January 19, 2006, with the primary goal of studying Pluto and its moons. After a 9.5-year journey, New Horizons conducted a historic flyby of Pluto on July 14, 2015. The mission provided the first detailed images of Pluto's surface, revealing a diverse and geologically active world with mountains, plains, and icy plains. New Horizons also discovered unexpected features such as Pluto's hazy atmosphere and evidence of flowing nitrogen ice. Following its successful encounter with Pluto, New Horizons continued its journey into the Kuiper Belt, where it conducted a flyby of a small, icy world named Ultima Thule on January 1, 2019. This encounter yielded valuable insights into the formation and evolution of objects in the outer reaches of the solar system. Now that we have seen these spectacular interstellar missions, let's take a look at the discovery Voyager 1 made in interstellar space. What fascinating discovery did Voyager probe find in interstellar space? During their interstellar expedition, the Voyager probes faced a significant milestone known as the heliopause, the boundary separating the Sun's influence from the vast expanse of interstellar space. The exact position of this boundary had long been debated, but thanks to astronomer Bill Gurney's projections in 1993, it was estimated to lie between 116 and 177 astronomical units, AU, with each AU equivalent to the distance between the Earth and the Sun. Gurney's estimations proved accurate when Voyager 1 reached the heliopause approximately 2 decades later, detecting the expected rise in plasma density. However, an intriguing puzzle emerged. Despite the increase in plasma density observed by Voyager 1, there was no significant change in the ambient magnetic field direction. This was unexpected because a transition from a region where the magnetic field originated from the Sun to one where it came from other stars should have resulted in a noticeable shift. Voyager 2 further added to the mystery when it reached the heliopause at the same distance as its twin, but failed to detect any magnetic field changes. These unexpected observations posed challenges to theoretical models depicting the behavior of the heliosphere and its interaction with the interstellar environment. The predicted synchronization between the heliosphere and the Sun's 11-year cycle did not align with the data gathered by the Voyager probes. Additionally, the solar wind, which fluctuates with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause, suggesting that the predicted position of the boundary should have been further out than 120 AEU. Nonetheless, the data collected by the Voyager probes have been instrumental in refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of the galaxy, likely triggered by nearby supernovae. These exploding ancient stars heated the surrounding area and removed electrons from adjacent atoms. The boundary between these regions can be likened to a turbulent seaside, characterized by mixed magnetic fields and small-scale changes near the heliopause, while negligible variations occur on larger scales. As for the future of the Voyager probes, their paths diverge, with Voyager 1 heading towards the constellation Ophiuchus and Voyager 2 making its way to the constellation Cetus. While some scientists predict a cosmic demise for the probes in 2030, they could potentially endure for millions of years, outlasting our own species. Perhaps one day they will encounter other star systems, carrying with them the golden record, a time capsule of humanity. Thanks for watching another episode of Beyond Discovery. While you're still here, click on the other videos you see on your screen right now.